So quantum computing, a bit of a sort of open-ended question, I suppose, but can you tell us a little bit about what it is, why it matters, and how, when, and where, which is an awful lot to ask you, but it's going to impact on businesses, the enterprise world, if you like, whether it's already happening or we're still waiting for it to make an impact.
Yeah, I will start by saying that quantum computing is still a research at work. I would say it's, let's say, quantum computing by itself is a paradigm. It's a theoretical framework, and now we are more and more into implementing it. But now that's when the technology is or will not emerge. And so, if really the quantum community is successful in implementing it, for sure it will be a big disruption, because it's proven, as I said, it's really a theoretical framework. And if we are able to implement it, then it will be a disruptor for many fields. But the question is how to have it, how to implement it, and with which limits. And that's today still a very open question. And so this is why I will re-insist it's still research at work.
And in actual terms of what it is, I mean, we've got obviously basic computing, we've got high performance computing, which has taken, I guess, computing that started in the research community, and now that's filtering through to business, sort of data, big data processing, stuff like that. So is quantum computing just, I say just, but is that another level of sort of performance beyond anything that's out there, or does it bring other things as well?
Well, so quantum computing is really a way to take advantage of some new physics. Well, new, I mean, as an implementation, some new physics, and then all is about yes, the advantage you can take from it. So there are some computations and very limited classes of useful computations that you can do by exploiting these laws of physics that can be useful in the real world. And so this is, I insist, it's still really research at work. We know that at the very atomic level, we can implement things that can be interpreted as a computation, and to which, at least on the paper, on the theoretical frame side, on the theoretical side, we can exhibit a computational advantage. And now it's about implementing it and see if, with the limits that we will meet, because it's very hard engineering, and we are at atomic scale. Within these limits, we will still have a computational advantage.
Okay, so at the moment, if you are somebody working in maybe a large enterprise, which tends to be the early adopters, what should you be doing? With quantum, should you be getting ready for quantum computing, understanding it, or kind of nothing and just waiting for another, I don't know, 12 months, 2 years until it starts hitting the market in some shape or form? What sort of advice would you give?
Well, as I said, so quantum computing, we know it's not, at least the advantage it will provide is not universal. So not all applications will benefit of it. And so the range of applications that will benefit from quantum computing is still unknown. And there is indeed a need for feasibility. Each business should make its feasibility and see if it is eligible, and with which limits, with which approximation limits. Meaning, for instance, if you see that indeed you could take advantage of this, but you would need 1 million qubits, then you can expect that it is not for tomorrow. If it is for 100 qubits, then it should occur in the coming years.
And in terms of the companies that are developing quantum computing technology, again, with computing, there are some familiar names. We know the people that produce the servers and even the high performance computing. Are the same companies behind the development of quantum computing, or are we looking at a new set of companies, or is it still too early for it to being sort of productized, and therefore it is literally just research organizations that are developing the tech? What's the landscape like?
Well, I would say that all major players in the cloud business are involved in quantum computing. So Google, IBM, Amazon, Microsoft, they are deeply involved in quantum computing. They spend tens of billions of dollars every year. They have their own research teams. They are building their ecosystem, and they are actively promoting their offer, trying to maybe lock a bit the market with their framework and so on, for sure. And then you have pure players, so startups, mostly startups, that are able for some of them to raise a huge amount of money, so 200, even 300 millions of dollars. And I would say that's the landscape. And of course, companies like Atos, involved in HPC, are also taking position. I would say we are the most advanced in the HPC landscape, because yes, you just have, I would say, as key players, you have Atos and IBM. HP is outside, and Lenovo also is outside. Intel tried early, they tried, but that's some annoying failures. But they're still active. They are now exploring new tracks, because of course they are involved in the hardware. So they did a first try on superconducting qubits, but seemingly it's a fail. And now they are looking at another option, which is silicon qubits.
Okay, and in terms of, obviously you've referenced Atos's involvement in quantum computing. You have developed, I mean, the main reason for us chatting today is you developed the QScore. So can you sort of explain what that is? I think I understand the basics, that it helps people to evaluate quantum computing opportunities, stroke possible applications. But can you give us a bit more detail as to what it is? Sure.
So QScore was really, at first it was built as an internal tool, because at Atos, we are not developing our own hardware. We are integrator. Our goal is to develop, or at least is to investigate if quantum technologies can bring something to high performance computing. And so we have signed several partnerships with proof players, with startups and even academic labs to test their technology. And our question is really when qubits will be useful for a practical problem, not just figures of merits of physicists, but really how useful can it be for a problem, and in which regime shall it be still useful? You may have a chip with 50 qubits, but in fact, when you play with it, you see that above 15 qubits, it's just useless. And so we built QScore really as at first as an internal metrics for us to qualify this technology that we may embed in our HPC. But we saw also a huge need from the customers, from the end users, who are a bit lost with this communication, with people claiming for a very various number of qubits. You see, for instance, D-Wave, they say they have 5,000 qubits, while Google said they have 53, and they are the most powerful chip. So they really just don't understand what's happening. And so our QScore is really built this way, that so it's a randomized benchmark that increase the number of used qubits on a chip until it considers that there is no computing advantage at all. So it's really an iterative benchmark. You start with a problem with a random problem with 2 qubits and 3 qubits, and then you analyze what the quantum computer returns, the qubits have computed, and from a statistical analysis, you say, no, at that point, I'm sorry, but your computation is just useless. I could do better with a very, very, very simple classical solution. So you cannot claim any advantage there.
Okay, and in terms of the work you've been doing already around this, I think the one or two industry sectors, I think medical and energy, for example, you've been involved. So can you just give us a bit of detail, yeah, without giving away any obviously trade secrets, but the sort of projects you've been involved with in maybe those industry sectors or others, as to what problems you're helping or looking to help them solve?
Indeed, we have customers. We're also providing services, but it's really research services with mostly large companies who are really in this initiative of feasibility, trying to identify if they can benefit, if some of their computational problems, mostly programs that are devoted to HPC today, are eligible to some kind of acceleration and so maybe a disruption. And so we help them do this feasibility study, and this is mostly, I would say, on either on chemistry problems, trying to compute very big molecules, or solving highly combinatorial problems. Typically, in energy management, you have very, very large problems that are going to be intractable to classical computers, and we look with them if there is a quantum alternative at first, if it's something that is computational, that can be computed by a quantum computer, and then what is this regime for an advantage, a real disruption in the computation. So this is the kind of studies we've been conducting with these players.
And it sounds like it's the classic, don't it? So it's sort of research and large enterprises that will be the early adopters. Can you see a time when it will have filtered down to the more of the sort of SME community, or do you think, to allude to your point earlier, that there are only specific applications that might ever need quantum computing, therefore it will remain a bit of a specialist sort of technology?
I think SME are also eligible, just that they may lack resources, of course, to devote to advanced studies like this, but they could benefit of it. And I would say today these early algorithms that are explored are I would say almost black boxed, meaning they could be exposed as a service in the cloud or whatever. They don't need huge development skills. So there is no need for large resources of programmers or whatever. It needs some time to do this feasibility. But these are even with very large players like Total. These are very small teams. There are maybe 2 or 3, and that's enough to do these studies.
And I think you alluded to in that answer that I was going to ask about, because I mean, high performance computing, for example, is being made available to most people as a service. Now, they might not be able to afford the huge upfront investment to buy all the necessary compute, but via the people you mentioned earlier, the Googles, Amazons, they can maybe access it. So you think quantum computing as a service will be a sort of practical? You mentioned those, the hyperscalers, they're presumably developing the technology for use within their organizations, but also to offer a service to customers as well, yes?
Yeah, indeed. And we also see pure players or startups that are asked by their investors to develop an as a service offer. So even these pure players could do this. And you see, for instance, Rigetti or some are coming in Europe. They are bringing this kind of as a service system. So, and then, of course, you have all the problems of confidentiality. Such that some, mostly of course, large players say that there is a need for them to be sure that they will be able to acquire this technology. Should their computation be very, very confidential, and wouldn't want to to expose it in the cloud, they say that that's an important requirement, that at one point they will be able to buy it and operate it by themselves.
And if we were, maybe in conclusion, if we were to have a conversation, which would be welcome, I must say, but in, I don't know, 6 months' time or a year's time, where, you know, with the best guess, and obviously the pandemic's shown us that trying to predict the future is maybe not that easy, but you know, assuming life returns to some kind of normal, say in a year's time, where would you think quantum computing would be in terms of its, you know, uptake?
We think, and this is shared with the community, that the earliest domains to demonstrate some advantage are in chemistry, material science, because there are applications that are very cheap in terms of qubits, meaning the problems are already quantum, so that you can encode them with very few resources on these small chips. So we expect indeed first disruptions in chemistry and all related domains, like material science, discovering new materials, maybe new molecules, small molecules, or a customer, for instance, Total is exploring quantum computing for molecules that can recapture CO2. And these programs can fit very well on a small qubit chip.
And I mean, I know the folks, for example, that are mapping the human genome and various things like that. Is that another potential way that quantum computing might replace the existing high performance computing? There'll be advances in that kind of activity.
Yeah, indeed. It's not been yet much explored, but we see more and more teams, genomic teams, exploring quantum computing. Indeed, because it's less natural than chemistry, because chemistry, you talk with the chemist, and in fact, just by describing its molecules, his molecules, you can map it on a quantum computer. It's already quantum. For genomic, it's less natural, but we see more and more work. We have Atos is operating an excellence center in the UK, which is a quantum and genomic expert center. And we also have our own research activity, but it's nascent. We need to bring together the experts, the genomic expert and the quantum computing experts.
Okay, well, it's been great to chat to you. I've learned a lot from a topic I wasn't that familiar. So, Cyril, thanks very much indeed for your time. Thank you.
You're welcome.